Missouri River is drawing some new attention tonight to the dangers open water presents.
Management and geology of the Missouri River allows citizens the peace of mind of not having to worry about catastrophic.
The stillness of the Missouri River has always been deceptive. Meandering calmly through the heartland of America, its waters hide centuries of geologic secrets beneath their muddy depths. But now, that veil has been ripped away by a recent satellite discovery that has sent ripples of concern through the global scientific community. Geologists have issued a red alert after satellite imaging revealed a massive rift, an immense fracture in the Earth's crust, lurking beneath the Missouri River basin. It is a geologic anomaly of staggering proportions, a scar beneath the Earth's surface that challenges long-standing assumptions about the region's tectonic stability. And what's more chilling, it appears to be growing. Before we start, smash the like and subscribe buttons for more updates. The satellite data was first collected through a high-resolution, ground-penetrating radar array combined with synthetic aperture radar imaging. These tools, usually deployed in remote sensing and earthquake-prone zones, weren't originally meant to focus on the central United States. But during a calibration run designed to test deep crustal structures, something anomalous appeared. Beneath the layers of sediment and centuries of glacial deposits was a fault-like rift, extending for hundreds of miles. Unlike the vertical faults that slice California or the traditional subduction zones along the Pacific Rim, this rift is wide, deep, and horizontal, cutting laterally across the bedrock like a torn seam in the Earth's fabric. What shocked geologists wasn't just the presence of the rift, but its location. The Missouri River region isn't typically associated with active tectonic deformation. Its quiet plains and slow hills have long been considered stable ground, far removed from the usual seismic suspects. Yet here, deep beneath the familiar landscape, is a chasm of instability. The rift's dimensions, as interpreted from the satellite data, show a width of nearly 30 miles in places and a depth plunging over 10 miles into the Earth's lithosphere. Its sheer scale has prompted comparisons to rift zones found in East Africa, or the ancient failed rift that underlies the Mississippi embayment. What's unfolding beneath Missouri is not simply a crack or a fracture. It is a rift zone in the true geological sense. Rift zones are areas where the Earth's crust is being pulled apart, and in the most dramatic cases, they mark the early stages of continental breakup. Although this process can span millions of years, the initiation phase, the point at which stress begins deforming the crust, can cause seismic shifts, subsidence, and volcanic activity. In the case of the Missouri Rift, there's no active volcanism yet, but subsurface modeling indicates significant mantle upwelling, hot rock pushing upward from the Earth's deeper interior. This kind of geologic behavior is not only rare in continental interiors, it's a clear sign that something enormous is happening below. Already, the rift's presence is beginning to reshape how scientists view the North American plate. The central United States, particularly the mid-continent region, was believed to be part of an ancient cratonic core, an area of very old, stable rock that hadn't seen major geologic upheaval in over 1 billion years. But now, with this newly discovered rift, that understanding is being rewritten. The old notion of this being a purely passive tectonic environment no longer holds. Stress must be building in ways no one anticipated, and it's raising urgent questions about what might come next. Initial stress modeling of the rift's dimensions has unveiled something even more disturbing. The rift isn't static. It is showing signs of active movement, measurable directional strain that indicates the crust is being pulled apart ever so slightly. The data suggests a widening of several millimeters per year, which doesn't sound like much on the surface. But over geological timescales, even minor yearly shifts can accumulate into catastrophic deformation. If this rift continues to develop, it could someday resemble the early stages of a new continental divide, a splitting of the North American plate from within. And it doesn't stop there. The surrounding region, including the states of Missouri, Kansas, Nebraska, and even parts of Iowa and Illinois, sits atop thick layers of unconsolidated sediment and glacial till, deposits that amplify seismic waves. Should movement along the rift result in fault slippage or quakes, the consequences would be profound. Unlike California, where buildings are engineered to withstand seismic forces, much of the Midwest has not prepared for this possibility. Infrastructure, from dams to pipelines to power stations, could be at risk. The Missouri River itself, a vital waterway for agriculture and transportation, could see its course altered or obstructed by land shifts caused by rift activity. Beyond the immediate seismic implications, the rift poses a deeper challenge to energy and water systems. A massive network of aquifers lies beneath the Midwest, including the vital Ogallala Aquifer to the west. Should the rift continue to evolve, pressure changes within the lithosphere could impact water tables and flow paths. This could alter irrigation systems, affect municipal water supplies, and even change the chemistry of groundwater in ways that ripple through the ecosystem and economy alike. At a time when the U.S. already faces mounting water challenges, any disruption in one of the nation's most productive agricultural belts is cause for grave concern. The satellite data also revealed unusual thermal anomalies along the rift's deepest sections. These thermal signatures suggest active heat flow from below, potentially driven by rising mantle plumes. If confirmed, this would mark a significant geodynamic shift. The presence of heat doesn't necessarily mean volcanic activity is imminent, but it does suggest that the crust in this region is thinner than previously thought, and that the mantle is interacting more directly with surface geology. This could drive further deformation, release gases trapped beneath the surface, or even trigger microseismic events. Seismic sensors across the region, many of them installed for monitoring mining operations or weather-related ground movement, have begun detecting a growing number of microquakes. These are tiny tremors, often imperceptible to humans, but they paint a larger picture when mapped together. The microseismic activity is not random, it's aligning with the rift's trajectory. In other words, the Earth is not only splitting but also shuddering as it does so. The buildup of such tremors, known in geophysics as seismic swarms, often precedes larger tectonic shifts. Whether these swarms are precursors to something more dramatic remains unknown, but their appearance is certainly not being taken lightly. What makes this discovery even more jarring is how recent the activity appears to be. Geological formations of this magnitude typically evolve over millions of years, but signs suggest that the rift has accelerated in the last few centuries, possibly even decades. Some theorists now propose that this could be tied to the retreat of glaciers after the last ice age. As the weight of the ice disappeared, the crust began to rebound, a process called isostatic uplift. Combined with deep mantle processes and subtle tectonic tension across the plate, the central U.S. might have reached a critical tipping point. Adding to the complexity is the potential role of human activity. Deep drilling, hydraulic fracturing, and large-scale groundwater extraction have all been implicated in destabilizing local geology in other regions. In the context of a newly forming rift, even minor anthropogenic impacts could act as catalysts, triggering events sooner than they might naturally occur. The subsurface pressures at play are immense, and any interference with groundwater systems or subsurface integrity could tip the balance in unpredictable ways. Scientists are now scrambling to install new instruments across the region. Denser seismic networks, GPS arrays to track ground movement, and deeper borehole sensors that can measure changes in temperature and pressure. But even with the latest tools, there's still so much that remains unknown. Rift dynamics are among the most complex processes on Earth, combining elements of seismology, volcanology, and fluid mechanics. And in the case of the Missouri River Rift, they're unfolding in a place where no one expected them. One pressing concern is how this rift could interact with existing fault systems. The New Madrid seismic zone, located just to the southeast of the Missouri River Basin, has long been known as an anomaly in the heartland. In the early 1800s, it produced some of the strongest earthquakes ever recorded in North America, including the legendary 1811 to 1812 sequence that caused the Mississippi River to flow backward temporarily. If the Missouri Rift is in any way linked to the broader stress regime that includes New Madrid, then the implications are staggering. Two unstable systems operating in tandem could create a corridor of seismic risk stretching across the American interior. There is also the broader geologic mystery of what lies at the root of this rift. Some geophysicists speculate that it could be a reactivation of an ancient failed rift zone, possibly connected to the Mid-Continent Rift System, a billion-year-old structure that runs beneath parts of the Great Lakes. These ancient faults never fully split the continent, but their scars remain, buried deep beneath layers of rock. If the Missouri Rift is tapping into one of these fossilized structures, it may be awakening something primordial and vast. Others hypothesize that this could be part of a newer, dynamic mantle process, one that has only recently begun manifesting. Hotspot tracks, similar to those that formed the Hawaiian Islands, could be pushing upward beneath North America's crust, reshaping it from below. If that's the case, then the Missouri Rift could be only the beginning, a surface sign of much deeper, more profound changes in the Earth's interior dynamics. What's unfolding now is a race against time and uncertainty. While the rift poses no immediate cataclysmic danger in the way of an erupting volcano or a hurricane, its implications are far more insidious. The Earth doesn't move quickly, but when it does, the consequences are irreversible. The Missouri River Rift represents a tectonic wildcard, a new force emerging in a region never prepared for it. Its slow but inexorable evolution may force a rethinking of how we monitor, build, and live across the middle of the country. The calm surface of the Missouri River, which for centuries has quietly nourished the plains and defined the rhythm of life across the Midwest, now floats above a deep and growing instability. The river has always been a witness to change, carving valleys, carrying sediments, shifting courses with each passing age. But this time the change is not of erosion or weather. It's coming from beneath, from within the Earth itself. The warning has been issued, the red alert sounded, and now, as satellites continue to scan the fractured crust and scientists probe the depths of the unknown, a silent countdown begins. One that could define the next chapter of America's geologic story. The unfolding revelation of the Missouri River Rift has not only upended existing geological paradigms, but has also opened a cascade of new investigations, implications, and theories, as scientists dig deeper into the data and deploy more advanced instruments across the region. What is emerging is not merely a tectonic curiosity, but the early evidence of a transformative geodynamic event in North America, one whose consequences could echo for generations. A significant point of interest now centers on the crustal stress redistribution taking place in and around the rift zone. When a region once considered tectonically stable begins to exhibit extensive deformation, it implies a larger scale adjustment in the underlying forces acting upon the North American plate. Researchers are modeling how the stresses from both the western boundary, where the Pacific plate grinds against the North American plate, and the eastern passive margin along the Atlantic seaboard might be transmitting pressure inward. The Missouri River Basin could be a natural point of accommodation, where the accumulated strain is finally expressing itself, breaking the crust apart in response to a complex tug-of-war between competing tectonic forces. This redistribution is not just theoretical. Early gravimetric studies have detected changes in local gravitational fields overlying the rift, subtle but measurable variations that suggest mass movement at depth. Such shifts typically occur when subsurface material migrates, either rising from the mantle or shifting laterally within the crust. These gravity anomalies can herald deeper movements that may not be visible through surface deformation yet, but signal active processes underway below the crust-mantle boundary. This has implications beyond mere geologic concern. It could affect everything from mineral migration to geothermal gradients, subtly altering the land's potential for energy extraction and agricultural productivity. Adding another layer of intrigue is the rift's possible impact on the magnetic field of the central United States. Paleomagnetic records extracted from boreholes and ancient rock cores in the region are being reanalyzed in light of the discovery. Preliminary results hint at localized magnetic anomalies, disturbances in the orientation of iron-bearing minerals that point to previous shifts or flows in the mantle underneath. This lends credence to the hypothesis that the rift is not an isolated surface feature, but a vertically integrated tectonic structure extending down through the lithosphere into the asthenosphere. The implications are profound not only for understanding continental drift, but also for long-term magnetic stability in a region that supports much of the nation's electrical infrastructure. Moreover, the hydrological implications of this rift could be more far-reaching than previously realized. The Missouri River acts as a drainage basin for thousands of tributaries, aquifers, and groundwater systems, many of which are interconnected in a delicate balance of recharge and flow. A shifting crust can deform aquifers, creating pressure differentials that lead to contamination, collapse, or flow reversal. In areas where the rift intersects major groundwater reserves, there is growing concern about the potential for subsidence or even aquifer rupture, a sudden discharge of underground water under immense pressure that could lead to surface collapse or rapid flooding in low-lying areas. This poses immediate challenges for civil infrastructure. Much of the Midwest's economic vitality depends on subterranean resources, natural gas, shale oil, and deep aquifers that supply municipal and industrial water. Pipelines, many of them decades old, crisscross this region, buried just feet below the surface. A tectonic rupture or slow warping of the earth beneath them could strain, bend, or snap these vital lines. It's not just about earthquake readiness, but about subsurface dynamics no one ever expected to need to model in this region. Utility companies are now being forced to reconsider the structural integrity of buried infrastructure that was never designed with active tectonics in mind. Urban planning models are also undergoing quiet revisions. While few city officials are speaking publicly about the threat, the implications being understandably sensitive, behind closed doors, regional planning commissions and emergency management agencies are reviewing building codes, evacuation protocols, and zoning ordinances. As more data flows in and confidence in the models grows, Midwestern cities may be compelled to adopt seismic resilience strategies once reserved for coastal or mountainous regions. This could mean retrofitting bridges and overpasses, redesigning water treatment plants to withstand ground motion, and even imposing new restrictions on high-rise construction near potential fault strands. While the discovery is rooted in geophysics, it inevitably intersects with human history. The land surrounding the Missouri River is layered not only with sediment and rock, but with the stories of indigenous peoples, settlers, and cities that rose and fell with the river's tides. Some researchers are now combing through oral histories from Native American tribes in the area, looking for accounts that might describe anomalous ground behavior or sudden changes in river flow. Incredibly, there are a few legends that speak of trembling earth and vanishing streams, stories that may, in hindsight, reflect localized seismic or hydrological disturbances linked to ancient movements along this newly revealed rift. Adding to the urgency of research is the distinct lack of historical data on how often, if ever, such rift activity has occurred in the area. Without a well-defined geologic precedent, scientists are navigating uncharted waters. Radiometric dating of rock layers around the rift is ongoing, with hopes of identifying past pulses of tectonic energy, small earthquakes, subsidence events, or even faulted sediment layers that might offer clues. If earlier episodes of rift activity occurred and then subsided, that could point to a cyclical process. But if this is the first time the rift has activated in a measurable way, the implications are more dire. A nascent geologic event whose outcome remains wholly unpredictable. As data accumulates, international scientific collaborations are forming to study the rift in greater detail. The Missouri Rift has become a focal point for tectonic researchers across Europe, Asia, and Africa, many of whom have studied rift zones in their own regions. Comparisons are now being drawn to the Baikal Rift in Siberia, the Rhine-Graben in Germany, and of course the East African Rift, each at different stages of continental extension. What makes the Missouri case unique is that it lacks the typical visual indicators of rifting. No high escarpments, no lava flows, no volcanic cones. It is so far a hidden rift, a stealth tectonic system operating beneath farmlands and riverbanks. This subtlety may be why it has gone unnoticed for so long, but it also makes it more dangerous. The lack of surface expression means the public has little tangible evidence of change. Unlike a volcano that rumbles and smokes or an earthquake fault that splits the ground, this rift betrays itself only in satellite imagery and slow, silent movement. It is an invisible threat, one whose consequences will manifest gradually until they don't. A sudden slip, an unexpected quake, a collapse of land along a hidden fault line, any of these could be the first overt sign the public receives that the earth beneath their feet is changing. And this leads to the broader philosophical tension now emerging among scientists, policymakers, and the public. How does a society prepare for a disaster that may never come, but might? The discovery of the rift forces a reckoning with long-held assumptions about safety and permanence. For decades, much of the country has relied on the idea that the Central Plains are geologically boring, unchanging, and stable. This belief has shaped where homes are built, where factories are sited, where power plants are located. Now that foundational certainty is cracking, both literally and figuratively. Colleges and universities in the region are already beginning to pivot. New research centers focused on intraplate tectonics are being proposed. Earth science departments are receiving a surge of grant proposals aimed at modeling deep crustal dynamics in the Midwest. Students and researchers alike are being drawn to the Missouri Rift as a case study that may define 21st century geology in North America. What began as a satellite anomaly is fast becoming a major scientific frontier. At the global scale, the Missouri Rift raises provocative questions about the very mechanisms that govern plate tectonics. If such a significant rift can emerge in the heart of a stable continent, then perhaps our understanding of continental rigidity is flawed. Maybe the Earth's lithosphere is more dynamic, more flexible, more prone to spontaneous rupture than previously imagined. This idea is gaining traction in the geosciences, and the Missouri Rift may be the first of many unexpected rifts to be discovered in the decades ahead as satellite and geophysical technologies become more refined. In a sense, the Missouri Rift is not just a geological feature, it is a message from the Earth, reminding us that we are not above its processes, that stability is not permanent, and that change can come from beneath even the quietest ground. It is a stark reminder of the planet's living, breathing nature, and of our own vulnerability in the face of forces that move far beneath the surface, slow and deep and relentless. As new sensors come online and deeper core samples are taken, a fuller picture will emerge. But one thing is already certain. The Missouri River Rift has changed the way we see the land beneath America's heartland. The questions it raises will take years to answer, but the urgency it introduces is immediate. There is no going back to a time when the Midwest was assumed stable. The Earth has spoken in its slow and subterranean voice. And now, the task is to listen. Carefully, scientifically, and without delay. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on the massive rift under the Missouri River? We want to hear from you. Thank you for watching, and see you next time.